Welcome back, 251ers. This is the last video of Chapter 3. Chapter 3. This is third. That's why I thought it was like third. I got confused with Chapter 3. Third and last video of Chapter 8. Sorry about that. Talking about waves. So we've been talking about waves, whether or not you realized it, mostly out in the open ocean. What makes waves, different types of waves, some definitions of waves, and some very simple math about waves. So that's all fine and good, and most of the ocean is the open ocean, so those are good things to learn. But most of us, for most of us, the ocean that we see is the ocean near the shore. And so we are going to spend the last lecture for this chapter talking about what happens when the waves meet the land in the surf zone. Okay, so you have your wave, right? And it's coming along. We talked about when the depth is greater than the depth of the seafloor, the water column is greater than half of the wave length, the wave cruises along happily, unaware that there is a seafloor, right? So these are basically these open ocean waves. We have our orbital motion of particles, and they're moving towards the shore. This is showing you the seafloor. Sorry, my voice is like cracking all over the place. Showing you the seafloor getting shallower. So out here, we're still deep enough that the wave base is above the seafloor, and so the waves will act as if there is no seafloor. Okay. When the wave comes upon the shoreline, and the depth becomes less than half of the wavelength, the wave touches bottom is the term. Touches bottom and the wavelength shortens. Feeling bottom slows down the waves, but increases their height since the energy lost by feeling bottom must be transferred somewhere. So basically what happens is you have a wave and it's coming along, right? And this is its wave base. But as it hits bottom, then that wave base is choked off and essentially pushes the wave up a little bit. So it increases the wave height. If you can see where we're going with this, eventually breaking, it also decreases the wavelength a little bit. It kind of scrunches it because it slows it down a little bit. So you're now increasing the wave height and decreasing the wavelength a little bit and slowing it down. So and then finally, so this is what happens when the wave touches bottom, wavelength shortens. Finally in the surf zone, the wave pitches forward and breaks. As the waves in front increase height and decrease wavelength, what do you think is going to happen now? They're going to lean forward a little bit. Whoa, whoa. Right, that was me leaning forward, trying to keep my balance. Because the wave crest is now traveling faster than the trough. When a wave height is greater than 1/7 the wavelength, we talked about this, the wave will break. So you can see what this happens here. We have nice big open wavelength form. As we're coming into shore, we start feeling bottom. The wavelength decreases, compressing the waveform, but also increasing the height at the same time. And then if you do that enough, it's getting skinnier, a little skinnier and higher there, and then skinny and greater than 1/7 wave height to wavelength ratio. And so then that's when it leans all the way over and crashes. And that is what happens in the surf zone. Hopefully that makes sense. You can see it, this is a figure from your book. You can see it all together in one figure. So again, waves have constant wavelength as they're coming in, and then they start touching bottom, the wavelength shortens, and finally in the surf zone the wave will pitch forward and break because that wavelength becomes greater than 1/7, maybe 2/7. Oh, then that's a problem, and then it's going to crash. Or break, I should say. Okay, so when the wave does finally break, there's a few different ways it can do this. A few different styles, let's say. So, and there are 3 that we talk about in this course. One is the spilling breaker. These break over a long distance. They occur on the smooth sloped shores, and they're meh for surfing. Smooth sloped shores, where do you think those happen? Let's think back a few chapters. Where do you have smooth sloped shores? We have them right here on the Gulf Coast. We also have them on the East Coast. We have them in passive boundaries, right? There's no tectonic subduction near the coastline, so you don't get these big rocky cliffs and steep beaches. So that's definitely not my phone. It's definitely not somebody trying to text me. Even more important than this text, 251ers, I'll find that out after class. So the spilling breakers, these would be pretty common on our beaches. Plunging breaker. Top of the wave outruns the bottom, creating an air pocket in which you can surf if you so desire. These occur over moderately steep sloping shores, and often they actually occur out to sea a little bit closer to shore. They are less common. So then finally, there's surging breakers. These build up and break right at the shoreline. Not enough time to reach critical steepness to break, so they just basically come right on the shoreline. These occur on shores with abrupt slopes. They're not good for surfing, but you could bodyboard them if you want. So plunging breakers, these are the ones that surfers like the best, because you can actually get in there, like they're doing in this plunging breaker. You can actually get in that air pocket. And again, these are going to be more common a little bit, not right on the shoreline, a little bit out to sea. This is what a spilling breaker might look like. Remember, spilling breakers, those are the breaking over the long distance, smooth slope shores. So this long breaking activity. And a surging breaker is kind of like, oh, these are one of the, do you like the sounds? I'm a wave expert. Something else that waves can do. If you have taken physics, you know that waves of light can do this. They can refract. Waves of water can also do this. Light and water, if you take any classes with Steve DeMarco, a physicist in our department, he will remind you light and water, it's all particles. Physics is the same. Just occurs at different rates. So friction with the seafloor as waves approach the shore will cause a wave front to become distorted or refracted as the velocity is reduced. Remember, as that wave comes in and it starts feeling the bottom, it's going to slow down. It's basically like, it's like if a running back is running with the ball, or any of the football players are running with the ball, and somebody tries to tackle them, and they're just, that kind of tackle where they're just holding on to their feet, right? That's going to slow that player down. It may not knock them down initially. They could drag them. Sometimes you see that happen, right? But that's going to, once you have something basically at the bottom of your form that's creating or experiencing friction, that's going to slow you down. So this causes a wave front to become distorted or refracted as the velocity is reduced. Refracted waves become increasingly parallel to the shoreline because parts of the wave deeper water catch up to those in the shallower water, right? So normally the wave crest is leading, but if does that make sense? Parts of the water, the wave in the deeper water, oh, I'm sorry, that does make sense. The wave crest is leading, but what happens is because the stuff that's in the front slows down, the stuff that's in the back actually can start to catch up because the stuff just in front of it slows down, and before the stuff behind it feels bottom, it catches up. Sorry, I was thinking about the shape of the wave, not multiple waves here. So the parts of the wave in the deeper water catch up to those in the shallower water, and it changes the direction of the wave as it moves, and it happens to change it so that it's parallel to the shore. This bending of the waves is called wave refraction. You can see a really nice example of it in this particular picture. I'm just going to go ahead and be honest with you. There's some things that are in the book that I guess we should be learning about, but I just don't care about this. Somebody must. It's not me. Moving on. Wave reflection is another thing. I guess these are things you should know in terms of the behavior of waves. This one's particularly good if you're interested in surfing. So just like waves as they're coming to shore can refract to face the shore, they can also reflect off of objects, or literally basically bounce off of stuff and be redirected. Wave reflection is bouncing off an obstacle, causes constructive interference. Now, if you're a surfer, that's where the fun part starts. So this is a picture I found online, this is a figure from your book, of a place in Southern California. By the way, if you haven't noticed, there's a lot of examples in the book from Southern California. The authors are from Southern California, so that's why they have so many examples from that area. So this is a place, a beach in Newport Harbor, which is in the Los Angeles area, Southern California, where you have a jetty here, and we're going to talk about jetties in a few chapters. And as the waves come in, they're coming in this direction, but you can see that the jetty is that direction. So they basically, in this little corner right here, they bounce off of the jetty and then go back this way. And then there's this area here called the wedge. And so the wave crest approaches the shore, it reflects off of the jetty, and then goes this way. And effectively, these waves bouncing off of this wall that go back that way meet up with the waves that are already going that way in phase. We get constructive interference and really good surfing. If you're good. This is also really dangerous because if you can see in the background, there's a bunch of rocks from the jetty right here. So you got to make sure you know what you're doing if you're going to surf the wedge. Apparently people get hurt there a lot. I've been told by my surfer friends. Okay, so that stuff is this stuff is important. So the last thing we're going to talk about is tsunamis. And scientifically, they are interesting as well, but they're important societally because they're massive disasters. So tsunamis, what I would like you to take away from this, tsunamis are not massive walls of water, as they're sometimes described. Rogue waves are massive walls of water. Remember, rogue waves, all of a sudden out of nowhere, you get constructive interference with a few waves together. So waves are going like this, and then out of nowhere, a big one kind of jumps up. So that's like wall of water coming out of nowhere. That's not what tsunamis are. Tsunamis are waves with huge wavelengths before they touch bottom. So those wavelengths they will decrease a little bit as they touch bottom, but their wavelengths could be up to 200 kilometers. That's ridiculous. So remember, for the wave to crash, 1/7 is the ratio. If 200 kilometers is on the bottom, what has to be on the top? It's got to be like 30, 40 meters before this is actually going to crest. Therefore, there are shallow water waves everywhere, right? They are feeling bottom everywhere. I'm sorry, 30, 40 kilometers, not 30, 40 meters, 30 something kilometers. So these are always feeling bottom everywhere in the ocean, but they have massively long wavelengths. They are caused mainly by seismic disruptions. So the most common story you hear is that there was a big earthquake, and then a few minutes later, there was a tsunami that came ashore somewhere in what you can imagine might be a pathway away of waves from that initial earthquake. They're caused mainly by seismic disruptions, which must be vertical, not horizontal, so not transform faults. These can't be faults going, two plates going like this, has to be plates bumping into each other. So, and usually they're caused by kind of a sudden shift or a sudden slippage is the term if you're really into the seismics or the description of science, I should say, of earthquakes. Tsunamis manifest as what appear to be massive tides. If the trough hits first, trough is the bottom of the wave. So if the first thing that reaches the shore in this 200 kilometer long wavelength is the trough of the wave, this is a public safety message. So if you ever see this, you know to go somewhere very high right now. If the trough hits first, the sea will go out unusually far. That's like a classic warning sign of a tsunami. Oh, I even say it's a classic warning sign of an approaching tsunami. You can see this in videos. I'm not going to show you videos of people dying in a tsunami because that's horrible, but you can see them on YouTube, and just to, if you want to get an understanding of the power of one of these events, there are good videos that are of scientific and societal interest online, so not just for drooling over horrible things happening to other people. And you can usually see that the first thing that you see is all of a sudden the tide goes out really far. Sometimes to the point where you could see like fish jumping around on the seafloor. If you don't know what that is, it's a very curious event. And then what happens right after that is that trough is countered with an extremely high crest that can travel inland And if it does so, it's going to flood everything in its path. Now, tsunamis move at a rate of a few meters per second. That's not that fast. What it is fast enough to do, though, is it's too fast for any human to outrun. You cannot outrun a tsunami. This is why so many people die in them. You need to either you can't outrun it on the ground, but you can get up high. So you want to get up at least 2-3 stories, if you can, as fast as you can, or possibly drive away. But even that is, remember, it only takes it only takes a foot to carry away a small vehicle. So you got to be careful. Most loss of life is related to a tsunami is from drowning as the moving water overcomes people on shore. And the scary part, remember, so tsunamis are massive waves. So there's going to be crests behind the first crest. It's oftentimes that the first one is not the tallest, maybe the second one, or the third one, or anywhere up to the 7th crest that could be the tallest one that does the most destruction. So because tsunamis are caused mostly by earthquakes, they can be caused by underwater volcanoes. Oh, somebody really wants to get my attention. Because they're caused mostly by earthquakes, and the largest earthquakes occur at convergent boundaries, right? Especially along the Ring of Fire. The largest tsunamis also occur along convergent boundaries, especially in the Pacific Ring of Fire. So, and this is a figure from your book showing you some of the largest tsunamis in the last 20 years, I think, since 1990. There was a really large tsunami that killed at least 1,400 people in Indonesia on September 28th, 2018, which is pretty recent, which is not included in this figure. And because that was pretty recent, there's a lot of video footage in particular from this recent tsunami. So that's something that's in the news right now, in the recovery from that tsunami. The two biggest in terms of death tolls, and actually looking at this would make this, depending on what the final number turns out to be, but in terms of death toll, 1,400 puts that as the third worst tsunami since 1990. So it was really horrible. The worst one ever was the one that occurred in 2004 in Indonesia. Killed the height of the wave. Oh my God. The height of the wave was 35 meters, 115 feet. You can't outrun that. And there were 300,000 people that lost their life in that. There was a movie about that not that long ago, I think with Ewan McGregor. My connection to that, even though it's really strange because it was in Indonesia, but one of my favorite bands, you may see me wearing a shirt every now and then of a band called Nasum, N-A-S-U-M, that I was madly in love with, still am. Their singer died in that tsunami. They're from Sweden, but he was on vacation in Indonesia and perished in that particular tsunami. So there were a lot of people that were vacationing that died, and there were a lot of people that are just from Indonesia that died in that. That was crazy. The one that maybe people remember better, even though this is a little while ago now, was the March 11, 2011 Tohoku earthquake and tsunami. That tsunami, the wave height was 40 meters, even bigger, 130 feet. 130 feet, a wave. For those of you that are on campus, 130 feet is about the size of the O&M building, the height of the O&M building. So imagine a wave height, the size of this building, 13 stories. So this in Japan is known as the 311 tsunami. It was caused by a magnitude 9 earthquake off of Tohoku. Magnitude 9, so that scale doesn't go very much higher than 9. I think there can be a 10, possibly an 11. For reference, this is the fourth largest earthquake ever recorded. That remains true. Fourth largest earthquake ever recorded. To get a feeling for what a magnitude 9 earthquake can do, the earthquake lifted the seafloor 7 meters. It moved the entire country of Japan more than 2 meters to the east. Oh, I'm sorry, to the east, further away from China. It's probably better for them. And it shifted the Earth's axis, the entire planet, sorry, almost cursed, entire planet, 10 to 25 centimeters, which doesn't sound like a lot, but one earthquake changed the axis of the entire planet and shortened the length of the day by like a tiny fraction of a second, but a measurable fraction of a second, just from one earthquake. So that is the just amazing power that these things can have. The resultant tsunami had a wave height of 40 meters and traveled as far as 10 kilometers inland. So again, remember, you're not outrunning this 40-meter wave height, which you can imagine why people call them, even though they're not necessarily a wall of water. You can imagine if you saw 40 meters of water coming your way, why you would describe it that way, and went 10 kilometers inland. So that you just, and you know, they're not going super duper fast, but the time between an earthquake and a tsunami hitting is usually the scale of minutes. So that there's really little to no escape from that. So I believe this is the last slide of the chapter. Sorry to leave it on a morose note, but this is a picture of the 311 tsunami near Iwanuma in the Miyagi prefecture. And just the reason that I show this picture in this class is I think that's, maybe I just speak for myself, but when I think of like a tsunami and a huge wave coming at me, I can imagine, you know, what that height might look like, but I have a really hard time wrapping my head around what that width looks like, right? And it's the entire area. So this is, you know, tens of kilometers of width of the coastline in Japan that you can see is just completely inundated by water. So you can see here these are multiple story buildings that are just completely underwater at this point. So these are really powerful events. Again, there was another one of these. These are natural events, so you know there's only so much you can do to prepare for them. You can't prevent them. So it's such as the nature of living on this planet. There was another one of these in September 28th, and so there's a lot of news coverage of that. If this is something that interests you, or if you want to give money to relief efforts for such an event. So that is the end of this chapter. Oh, guess what? Guess what? We are now more than halfway through the class. So there's 16 chapters, but plus the intro chapter. So having arrived at the end of chapter 8, we are beyond the halfway point of this class. So that might be, I don't know, you know what, 251ers? You tell me if the glass is half empty or half full. Depends on it. If you love it, maybe you're like, oh no, there's only less than half of the class left. If you hate it, you're like, thankfully this class is almost over. Well, it's not almost over. There's still about half left. But we're doing it. We're making progress. You're doing great. So proud of you. The next chapter is tides. It's okay. We'll do it. We'll make it fun. And until then, just, you know, go out there, be good people, and I will see you when we talk about tides, not the laundry detergent. I don't think I could fill a whole lecture, much less multiple lectures, talking about that. But you know, when the water's moving because of the sun and the moon, that thing, tides. That's what's next, and see you then. Exit this way.